включено. Okay, let's start. Sorry that we don't have streaming today. We are just recording, and later we shall put this record on the site. Okay. Last time we proved following theorem. So let's take a polynomial of two variables with complex coefficients and assume that f itself and its derivatives, partial derivatives, do not vanish simultaneously on some domain. These are assumptions. Then zeros of this polynomial defines a manifold. Exactly speaking, complex manifold. Well, yeah, sometimes manifold, the definition of manifold requires connectivity, but here we do not assume any connectivity. And yeah, we use some lemma in the proof of this theorem, which is actually the implicit function theorem. And according to that lemma, if, for example, derivative by w doesn't vanish, then we can use z, another variable, as a coordinate. Of course, if okay, if this does not vanish, then we can use w as a coordinate. Of course, locally in a neighborhood of this point. So let's apply this theorem to this simple polynomial. Then this is what we discussed last time. We constructed the Riemann surface for square root by gluing together two complex plane in this way, and later we redefined that Riemann surface as the zeros of this polynomial. And we can apply the theorem because, let's see, this is just -1. So, since this derivative doesn't vanish anywhere, so this assumption automatically satisfied, and we can use we can say that this Riemann surface is one-dimensional complex manifold. Well, today, Riemann surface is another name of one-dimensional complex manifold. But anyway, and moreover, when W is not equal to 0, or since W square is Z, when Z is not equal to 0, then this condition is satisfied. In fact, except for this point, we can use Z as a local coordinate. But at 0 here, Z cannot be a coordinate. But instead, we have this, so W can be used as a coordinate in the neighborhood of this point. And well, yeah, last time, why did we construct a Riemann surface for square?
Sorry.
Yes.
Are coordinates on where Riemann surface?
Local, let's say local.
But how can we that Z is 0 and W is not 0? We have that.
Oh, so. So at this point, we cannot use Z as a coordinate because here at the point 0 it coincides. And the reason why we wanted the Riemann surface is that we want some reasonably convenient definition of square root. In this case, just a projection to the second component is the square root. In fact, because here we have such an equation, so W always satisfies this. And of course, at any point except at 0, this projection or to W coincide with the previously defined square root, of course. And when z is equal to 0, then, of course, both of the coordinates are 0, so it just gives 0. And moreover, it's a nice function because this is nothing but a projection. So it is, of course, homomorphic. Well, yeah, square root is important example, but probably it's too primitive, simple. Yes?
If we define a projection on Z, then it will be not homomorphic in certain cases.
Yeah, except at 0, well, it's good. But at 0, we have to use W as a coordinate on this manifold. But so this is W square, and so it is homomorphic. Yeah. Next example. The final goal is, let us recall. The final goal is the elliptic integral. And we need a square root of a polynomial of degree 3 or 4. But before that, let's consider such a function. Well, in this case, what should we do? Last time, we saw that square root changes its sign when we go around 0. Right? And then And that's why we need to glue two sheets. In this case, where is the problem? Well, yeah. It has two zeros. For example, around +1, this part doesn't do anything bad because it's close to square root of 2, no, not there, or minus. So, well, this part behaves like the square root around 0. So, if we go around this, it changes sign. If we go around -1, then because of this part, this function changes sign. And if we go around, for example, in this way, then yeah, if you trace the change of the value like this and like this and like this, then you will see that if z gets back to its original value. Well, yeah, in this picture we can explain this. Here -1, here -1, so -1 times -1 is +1. Anyway, in this case, at +1, we need some cut. At -1, we also need the cut. But when we go like this, then we do not have to change the sheet. So the reasonable construction of the Riemann surface for this function is gluing two complex planes like this. This side is glued to this side. This side is glued to this side. And the resulting surface might look something like this. Give me again, at +1 and -1, we have 0, only one value. So they are exhibitions. We glue together and add these exceptional points, or it is often called branch points, because here we have branch, two sheets. So this is the Riemann surface of this function. Or in this way, this is Riemann surface. Or since square of this function is 1 minus z squared, we can use this polynomial to define the Riemann surface. Well, let's check whether we can apply that previous theorem. Derivative by z is 2z. This is 2w. So this triple does not vanish. Anywhere. Well, yeah, the simplest proof is that if these two derivatives vanish, then z and w are 0. But at that point, f is equal to -1, so it doesn't vanish. Therefore, this is one-dimensional complex manifold. And moreover, we can use z as a coordinate if this derivative does not vanish. Namely, around a point such that w does not vanish. This means, yeah, when w is 0, z is equal to +1 -1. So this condition means that is namely, except for these branch points, we can use z as a coordinate, as is expected from this picture. Namely, except for these points, we can take a small domain on which we can use z as a coordinate. But when w0 is 0, we cannot use z as a coordinate, so at these points. We cannot use Z as a coordinate. Instead, we should use W. Okay, and yeah, as before. Function square root of 1 minus Z square is interpreted as a projection from this to this. Okay. Okay, I just erased and redraw the picture. I drew such a picture. Here, it seems that we have some intersection on this segment, but actually we do not, because well, this is such a set, and actually on this segment there are two Z's and W's which satisfy this in this condition, this equation. Therefore, this picture is not good for studying, for example, geometry or topology of this Riemann surface, one-dimensional complex manifold. So what should we do? Well, the natural or real true form can be seen by gluing two sheets not like this, but let's put this sheet upside down.
You mean that we conjugate?
No. Just well, you can look on this side and you will see use a complex number. Just a just a usual complex number. Maybe. And in this case, where should we glue? This side corresponds to this side. Or we just put this, rotated this way. This side, glue them. Then this side, this, something like this. and this and this. You see that how to say, the upper side of this should be with the lower side of this, and so this picture, this going really do the work. Then what happens? You see, the orientation of this side and this side are compatible. What is this? This is just a cylinder. So this Riemann surface has a topology of this cylinder. And yeah, what do we want to do on this cylinder? Well, yeah. We want to consider integrals of this kind. And for example, in this case, well, the thick integral of the first kind was something like this. So for the moment, let's forget this part and consider such an integral. Or, yeah, first, before integration. Consider this one form integrand. Of course, this should be considered on this manifold Riemann surface. And exactly speaking, to avoid multivariateness of square root, we should regard this omega as such a manifold on this Riemann surface.
Do you mean del d omega or
well, here? Well, this is W. How do we solve?
That's this omegas are different. Yes?
This and this is different. Sorry. Well, yeah, very, I should use very different letters, but well, this is some convention. Yeah, well, we often use omega for one form, and here, yeah, W is probably better, good partner. So yeah, please pay attention to this and this. Okay, so, well, yeah, this is a nice expression, except that 0. Well, of course, in this, when the denominator doesn't vanish, then this is a homomorphic one form, namely a coefficient of dz is homomorphic. Fine. Then, how about this point? Is this one form singular at this point? Because actually, no. At this point, we cannot use z as a coordinate. So we have to rewrite this in terms of w. Namely, this dz cannot be used at this point. Well, we know that w squared minus square is equal. So let's consider differential of this equation. Then we have this equation for one forms. And this holds when z and w are not 0. And therefore, dz equal to minus this means that this one form is equal to, and just replace dz with this. And recall that this point corresponds to such a point, namely at this point, denominator does not vanish. Therefore, this defines a homomorphic usual, not diverging one form, even at those branch points. Namely, except these points, we have already a homomorphic form, and we can continue extend this homomorphically even to those points. So this expression defines a homomorphic one form on the whole Riemann surface R. So that's about the integrand. When considering integral, we need to specify contour. Well, we'll call some complex analysis. Let's assume that f is an entire function, namely a homomorphic everywhere on the. Okay, so this is a homomorphic function on the whole thing. Then, when we integrate this one form, the value does not depend on the contour. Because of Cauchy's integral theorem. How about, well, this is on C. How about with this one form? We are considering this on the Riemann surface. Well, for example, we can consider such a path, or we can consider such a path. Well, actually, what is the difference of these two paths? Well, since this is a homomorphic one form, at least except around this segment, we can deform this contour like this. First, go straight forward to Q, then go around in this segment, and go to Q. on this cylinder expression, this is something like this. This is something like this. Namely, well, in addition to this straight path, we go around around the cycle of this cylinder. And therefore, if we call this cycle A, well, this not depends on the size of this contour because of the Cauchy integral theorem. So let's see. Actually, these two integrals varies different by the integral over this cycle. For example, if we take a contour something like this, first on the upper sheet and then go to the lower sheet and return to the upper sheet and cut this. Wow, this means that first go across this line and this circle, and then this part is the lower sheet, this part is the upper sheet. So this is something like this, and if I'm correct, also and here we do this, and well, probably this. Anyway, this is equal to, well, homotopically equal to such a contour, namely something like this. So if we call this C to the second contour, then these two integrals differ by minus integral over A. Well, so probably you have already understood that this is a problem of homology. Well, I do not need any exact definition of the homology group and manifold and so on. So let's define or maybe even better to put quotation marks. This is a quotient of a free abelian group generated by closed curves in this manifold over certain equivalence relation. And well, for example, not for example, and the definition is something like this. This is well, this is another closed curve. Then this means C prime. Yeah, well, yeah, they have common point, common starting point, and 結果 this is C inverse, namely this is C with different orientation and point. Such a composition of closed curves is a union of boundaries of domains. If you know or the definition, it is Z1. This is the subgroup of Z1. Sorry, Z1 and B1 boundary, and so factorizing the group of one cycles by one boundaries, then we have a homology group. Well,
question.
Yes.
What is boundaries of domain in Russian?
Граница области.
Открытых областей? Или что это имеется в виду?
Точнее говоря, well, it's a this domain is actually the images of disk by continuous map D and boundary means the image of the boundary circle of this. Yes.
Образов дисков.
Да. И без этого, без внутренности, тогда это означает цветажи.
By continuous map or by
But
homeomorphism?
by continuous map. It is.
Why the image of boundary will be exactly the boundary of the image?
Not exactly. And the difference is counted by this. So for example, yeah, in this case, such circle is exactly boundary of this circle. Disk. But such a circle cannot be a boundary or union of boundaries of disks. If this is something like this, sphere or whatever, then we can take such a disk and this circle is a boundary. But in our case, we don't have such a cap. This is just a cylinder, and therefore one element remains, not factorized. Therefore, sorry, not homology, but homology group of a cylinder is generated by this circle, and it is a rank 1 abelian group of a. So I don't want to make a lecture on topology. So just if two closed curves are homotopically equivalent, namely, which means that we can continuously deform closed curve C to this closed curve C prime. Then these two curves are equivalent in this sense. Or if we have for example, on the cylinder, such a curve can be continuously moved to this. So we have just one representative of this equivalence class. And such a curve is not equivalent to this, but also, and this is composition of two such circles. So it's two. Anyway, in this case, homology group has such an expression, and any curve connecting P and Q is equivalent to the simple straight segment plus well, yeah, maybe such notation is better. And therefore, well, so this means that we connect C and the inverse of this scissor. From this, we have such a equation, identity for integrals. Therefore, this quantity, this integral is quite important for this. And it is called a period integral, or just period. Period integral of this one form over the cycle A. Let's compute this explicitly. A is just like just like this. But as I told you, we can use Cauchy's integral term, and we can just compute such an integral, namely, or such an integral. Usually, in such a case, they just cancel out because we have different orientation, and so they are just minus. But in our case, it is not, because we are integrating here on the lower half plane, and here we are integrating on the upper half plane. And recall that if we go around this point, the square root changes its sign. So this is just I use x because we are now integrating on the real segment from -1 to 1. And this one is from 1 to -1 and minus. Well, let's take positive square root on this segment. We are now in the real world, so our 1 minus x squared is a positive number because x is between -1 and 1.